Okay, so that brings us to Kramer's rule, then Theorem 7. So if A is an n by n invertible matrix, right, so it's important for us, we can only apply this theorem if A is invertible. So if A is an n by n invertible matrix and B is an n by 1 column vector, then we can go and solve the system AX equals B. We can solve each x. The ith x is simply given as the determinant of AI divided by the determinant of A. Now, what is the determinant of AI again? Remember, you take the matrix A, you delete the ith column, and you replace that column with a vector B. And then you take that matrix and you go and work its determinant out. And then also to multiply that with 1 over the determinant of A. Alright, so let's look at the derivation of Kramer's rule. So essentially what we want to do is we want to solve the system X equals A inverse B. Now, by the adjoin method, we can find the inverse of A as the adjoin of A divided by the determinant of A. So we can replace A's inverse with that quantity. Alright, so taking the adjoint of A multiplied by B multiplied by the scalar 1 over the determinant of A, that is equal to that given product on the right hand side. So all we did there is we replaced the adjoint of A with what it is, and remember what's the adjoint of A? You take the cofactor matrix and you take the transpose of that matrix. So that's the adjoint of A. And then you multiply it with a column vector B. So what we're going to do now is we're going to multiply that that adjoint matrix with the column matrix B, and that gives us an expression for X. Now, if we look at the matrix on the right-hand side, that column matrix, the jth entry in that column matrix is given by this cofactor expression, B1, C1j, B2, C2j, up until Bn, Cnj. So that's the jth row entry in that matrix. So therefore, the jth x in X, the column vector X, is given by B1, C1j plus B2, C2j, up until Bn, Cnj, divided by the determinant of A. So that is the jth x that I've solved. Okay, so recall what the definition of A subscript j was. It's the matrix that I get from A by deleting the jth column and replacing that jth column with a vector B. Note that A subscript j differs from A only in the jth column. So what is the significance of that? The significance of that is that the cofactors of the entries B1, B2 up until Bn, those entries are exactly the same in A subscript j as the cofactors of the corresponding entries in the jth column of A. Alright, so how do we work out the cofactors of the entries in the jth column of A subscript j? You take the jth column of A subscript j, then for the first cofactor entry you delete the first row and you work out that cofactor entry. Then for the second cofactor entry you delete the second row in the jth column, and you carry this process through right till the end, the last row. You delete the last row in the jth column of A subscript j and you get your last cofactor. Now you can do exactly the same for A. You work out the cofactors of the entries in the jth column of A by deleting the jth column of A and then subsequently deleting the rows as you move along. Now the cofactors of the entries in the jth column of A subscript j is exactly the same as the cofactors of the entries in the jth column of the matrix A. Alright, so now we can go and work out the determinant for the matrix A subscript j by just using all the cofactors we worked out for the entries in the jth column. So we expand along the j's column for the matrix A subscript j, and we get that the determinant of A subscript j is that expression on the right-hand side. Recall that we solved for x subscript j as that expression on the right-hand side. So now we just substitute back for the determinant of A subscript j, and we get that x subscript j is the determinant of A subscript j divided by the determinant of A. Okay, so let's look at some examples of where we can use Kramer's rule to solve a system of linear equations. So I'm going to do example 1, and I'm going to leave example 2 and 3 for you students to do on your own as an exercise. Okay, writing down number 1, the system of two equations with two unknowns. You can write that system in the form ax equals b, where A is given by this matrix, x is given by that matrix, and b is given by that matrix. Okay, and now we construct the matrix A1. So we take A, we take the vector 3, 4, and we delete the first column of A and replace it with the vector 3, 4, and that's A1. Then we construct A2. We take A again, we delete the second column of A, we take the vector 3, 4 and replace the second column of A with 3, 4. And that will be the matrix A2. Right, then we calculate the determinant of A1 and the determinant of A2, and also we calculate the determinant of A. And then we use our Kramer's rule formula to solve for x1 and x2 via substitution. Let's do some tutorial problems. I am looking forward to these problems. I eat them for breakfast. That was really good. Okay, let's get going. Alright, let's look at the first problem. So we're given 3 points in the xy plane, and we form the matrix A as described there, and we are asked to show that those 3 points are collinear if and only if the determinant of that matrix A is 0. Okay, so what does it mean for 3 points to be collinear? It means the 3 points lie on a single straight line. Alright, so let's first assume the 3 points, point 1, point 2, and point 3, they're all 3 of them are collinear. Now remember, there's the straight line formula between 2 points in the xy plane. You take the y component of the one point minus the y component of the other point, and that's equal to the slope of that straight line between the 2 points multiplied by the difference between their respective x components. So applying that to the straight line segment from point 1 to 2 and then from point 2 to 3, we get those two equations, 1 and 2. Now the slope of these two straight lines have to be exactly the same. That's why they are both alpha, because the 3 points are collinear. Okay, now let's look at the first case. What happens if alpha is 0? If alpha is 0, then from 1 and 2, it follows that y2 is equal to y1, y3 is equal to y2. And then you take the matrix A, where you see a y1, you write a y2. Where you see a y3, you write a y2. And you have that if y2 is 0, your determinant of A is going to be 0, because it's got a 0 column. Okay, so let's look at the case where y2 is not 0. Then A is going to have 2 proportional columns. The second and third column of the matrix A are going to be proportional. In other words, one is a scalar multiple of the other. Now we know from previous laws that if a matrix has two proportional columns, then it is definitely going to be have a zero determinant. Okay, so now we construct the matrix B from the matrix A by taking the last column of the matrix A and multiplying that with alpha. Now note that the determinant of B is alpha times the determinant of A by our previous determinant laws. So therefore, we can actually just show that the determinant of B is 0, because if the determinant of B is 0 and the determinant of B is equal to alpha times the determinant of A, then it follows that the determinant of A is 0. Okay, now we can work out the determinant of B. So you take B and you expand, work out the cofactor expansion along the second column. So you're going to cancel the second column, and then you're going to run through all your rows, and you get your expression for the determinant of B along the second column. Okay, now we consider again the expression that we got for the determinant of B. And now remember the two expressions 1 and 2. You take the second line of the determinant of B's expression, and where you see an alpha x3 minus x2, you substitute a y3 minus y2 from the second equation. And where you see an alpha x2 minus x1, you substitute y2 minus y1 in your determinant of B expression. Okay, so essentially what you did was, in the determinant of B, the second line, you got rid of the alpha x3 minus x2 on the far left, and you got rid of the alpha x2 minus x1 on the far right, using expressions 1 and 2. Okay, now having eliminated those terms as I described previously, you go to your next slide, and you do some simplification until you get to the last line, the minus y1, y2 plus alpha y2, and so on and so forth. Now, what happens if you add those two expressions? Alright, so what happens if you add those two expressions? On the left-hand side, you get y3 minus y1, and on the right-hand side, you get alpha multiplied by x3 minus x1. So going back to your determinant of B, the last line, you can go and substitute alpha x1 minus x3 with your expression that you got from adding 1 and 2. Right, now going further, the last line of that determinant expression from the previous page, remember we added 1 and 2 to get y3 minus y1 equals alpha x3 minus x1. Plug it back into that last line, do the simplification, and eventually you'll see that the determinant of your matrix B is equal to 0. Okay, now we're going to assume that the determinant of the matrix A is equal to 0, and then we're going to prove that our three given points are collinear. So assume the determinant of A is 0, and now we're going to prove that our 3 points are collinear. So how do we prove 3 points are collinear? You take the 3 points, you fix 1 point, and you take the straight line from the 1 point to the fixed point, and you take the straight line segment from the other point to the fixed point. And now what you need to do is you need to show that those two straight lines have the same slope. And when they have the same slope, those 3 points are going to lie on a straight line. So again, we indicate the one straight line to have a slope of alpha, and the other straight line to have a slope of beta. And again, you use your straight line formula. You take 2 points. To find the equation of the straight line through those 2 points, you take you basically note that the y component of the one minus the y component of the other point is equal to the slope of the straight line multiplied by the x component of the one point minus the x component of the other point. Okay, so let's first check what happens if the slope of the second line, beta, is equal to 0. Now, if alpha is equal to 0, then the slope of the first line is also 0. Then it's going to mean that y2 minus 1 is 0 and y3 minus y2 is 0. Now, if you take, this is going to imply that the y component of your 3 points, they're all going to be the same. And this is going to imply that those 3 points must lie on a straight line. They lie on a horizontal straight line. And now we basically may assume that alpha is not 0 because we looked at the case where alpha is 0. So now remember, the matrix B is a matrix obtained from the matrix A by multiplying the last column of A with alpha. And remember, we can work out the determinant of B by using the cofactor expansion along the second column. So that gives me an expression for the determinant of B written down there. Now also recall that we said that the determinant of A is equal to 0. Now the determinant of B is equal to alpha times the determinant of A by a determinant law. And therefore, because the determinant of A is 0, the determinant of B is also 0. Remember, if you obtain a new matrix by multiplying the column of an old matrix with a scalar alpha, then the determinant of the new matrix is going to be the scalar alpha times the determinant of the old matrix. Okay, so we have now the fact that the determinant of B is equal to 0. We equate that expression for the determinant of B we obtained, we equate that to 0. Now because beta is 0, we have that y3 is equal to y2 from our second expression. Now you take your expression for the determinant of B, and where you see a y3, you change it to y2, and you do your simplification until you are left with alpha multiplied by x3 minus x2 multiplied by y1 minus y2 equal to 0. Therefore, either x3 minus x2 is 0 or y1 minus y2 is 0, because remember we said alpha cannot be 0. We looked at the case when alpha is 0. Now if it happens that x3 minus x2 is 0, then the 3 points are going to be collinear. Because remember we said that beta is 0, which means that y3 is equal to y2. And because of this fact, and the fact that x3 is equal to x2, means that your second point is equal to your third point. So if you take your 3 points, point 1, point 2, and point 3, you can draw a straight line between those 3 points because 2 of those points are the same. Okay, so the only other option is for y1 minus y2 to be 0, and so y1 is equal to y2, and because beta is 0, we have that y3 is equal to y2. So then again, your 3 points have the same y component, and therefore they are on a straight line. We look now at the cases where alpha and beta are both 0. So we may assume alpha and beta are non-zero. So we know now that alpha and beta are non-zero. So you take your original expression you got for the determinant of B, which is the cofactor expansion along the second column, and remember we equated that to 0. So you write that expression down, and you multiply the whole expression through by beta. So you get your alpha beta terms there in the second line. We want to eliminate alpha beta x3 minus x2 and alpha beta x2 minus x1 from that expression, the second line of the determinant of B expression. And we take our original two straight lines 1 and 2 and we manipulate them by multiplying the first line with beta and multiplying the second line with alpha on both sides. So multiply the first straight line equation with beta on both sides and multiplying the second straight line equation with alpha on both sides. And then you get those two equations in the last slide for alpha y3 minus y2 and for beta y2 minus y1. You can also then find an expression for alpha y3 minus y2 plus beta y2 minus y1 by adding the right-hand sides of those two equations. Now we're going to replace alpha beta x3 minus x2 in our expression with the expression alpha times y3 minus y2. Okay, you can use the expression for alpha beta x3 minus x1, that sum, to replace alpha beta x1 minus x3. Then you can use the expression for alpha beta x2 minus x1 and you can replace alpha beta x2 minus x1 there in that expression. Okay, in the next slide we simplify a little bit. Going back to our list of three equations, we use the expression for alpha beta x3 minus x1 and we substitute it there into alpha beta x1 minus x3. From there on we do simplifications in algebra until we get to the last line of the second slide. Okay, and then we simplify some more and we factorize until we get to the expression alpha minus beta multiplied by y3 minus y2 multiplied by y1 minus y2 equals 0. Okay, so either alpha is equal to beta or y3 is equal to y2 or y1 is equal to y2. If y3 is equal to y2, then by the second straight line equation we get that x3 is equal to x2 and so the 3 points are collinear. If y2 is equal to y1, then by the first straight line equation we get that x2 is equal to x1 and so the 3 points are collinear. So the only option is for alpha to be equal to beta. Therefore the slope of your two straight lines given by 1 and 2 are exactly the same, so the 3 points are collinear. Okay, so let's look at the second problem. Use determinants to show that for all real values of lambda, the only solution of that system is the trivial solution. That is where x is equal to 0 and y equals 0. Okay, so there you have your system, your two equations. Then what you do is you get your lambdas on the left and the zeros on the right. And that little system there corresponds to the matrix system Ax bar equals 0. A is the matrix 1 minus lambda minus 2, 1 minus lambda plus 1. X is the vector xy and 0 is the vector 0, 0. Okay, then we work out our determinant of A and we find that it is lambda squared plus 1, which is always bigger than 0. It follows that determinant of A is not 0 and so A is invertible. Since A is invertible, we can solve the system Ax equals 0 for x. We can solve x as A inverse 0 times 0, which implies that x is 0 and y is 0 for all lambda. Okay, let's look at the last problem. Find all scalars C1, C2, and C3 such that the sum of the scalar multiples of the vectors on the left is equal to the 0 vector on the right-hand side. Okay, so you set up your three equations with three unknowns, C1, C2, and C3. So you go according to the x component to set up your first equation, then according to the y component, your second equation, and then your z component is going to be your third equation. Now that corresponds to the matrix system A C bar equals 0 bar, where A is defined as that 3 by 3 matrix, C is defined as C1, C2, and C3, and the 0 matrix is 0, 0, 0. Then we want to calculate the determinant of A. So you take the matrix A and you change the matrix A to A1 by taking A and adding minus 2 times the first row to the second row, and that gives you a new matrix A1 which has the same determinant as the determinant of A. We now form a matrix A2 by taking A1, changing the third row of A1 by adding a third times the second row of A1 to the third row, and that gives us A2, and the determinant of A2 is the same as the determinant of A1 by sections 2.1 and 2.2. So the determinant of A2 is minus 6, which then leads to a determinant of A being equal to minus 6. Alright, so because the determinant of A is minus 6, the determinant of A is not 0, and therefore it's invertible. So we can take the system A C bar equals 0 bar and solve it as C bar equals A inverse 0 bar, which is 0 bar, and that implies that C only has the trivial solution. So therefore C1, C2, and C3, they're all equal to 0. Those are the only real numbers that satisfies the equation.